Good morning, everyone. That's my pleasure to present you today a methodology coming from EU called Smart Grid Architecture Modeling and Mapping that is pushing forward a methodology to make sure that people coming from different disciplines will make the smart energy system a reality. My name is Raphaël Kerr. I'm coming from France, from École nationale supérieure de l'énergie, de l'eau et dans l'environnement, including in the university called Institut Polytechnique de Grenoble, and which is part of University Grenoble-Alpes. The content of the lecture will be today, first part about smart grid, so giving you general definition and communication needs. The second part will be about a optimal coordination of active distribution regulating means, which will be, let's say, a very specific use case of smart energy systems. And of course, I will finalize my presentation with a conclusion. At the end of the lecture, the student should be able to do several things. That's what we call learning outcomes. So at first, you should be able to describe the smart grid concept with the 3 revolution paradigms. You should be able to list the axis of smart grid architecture modeling concept. You should be able to select the relevant objective function for an advanced distribution automation function. You should be able to support the selection of relevant protocol and data model, to discuss the relevant business case for a given advanced function, and you should be able to construct the various layers for a given automation function. So let's start with the general definition and communication needs. At first, let's talk about the new concept, new paradigm that we are all facing all around the world. At first, we have a world population that is rising, and of course, the load that is still growing because of new people being connected to the grid. We are having an issue about, let's say, fossil fuel resources that are becoming more and more expensive, more and more complicated to get. We are having some threats that are both physical and cyber threats, and of course coming with climate change that is pushing forward some new concepts and some new revolution in the energy sector. Associated with the aging of the infrastructures, the fact that our power systems are getting older and older, the fact that there is more and more stochastic production due to renewables, some new loads that are appearing, such as electric vehicle or plug-in hybrid vehicles, and 2 concepts that are really sociological, that are, the first one is not in my backyard. Okay, I fully understand that there is some issue about energy, but I don't want to have a wind farm, for instance, just close to my house. And as well, the plug behind what is behind the plug, it's in fact, I don't know, and I don't care. And I'm not ready to pay much more for what is already with a good quality. But there are some opportunities as well. And the first thing that we'll discuss today is about some communication means. We are really able to coordinate the whole smart energy system thanks to, for instance, new intelligent appliance. Let's think about smart homes, for instance, but as well some large R&D programs that are pushed forward thanks to a large institution and different politics. Okay, so let's start with the new paradigm and let's try to understand what are the new challenges for our power systems. And at first, of course, the landscape, as it was in the past years, is the following. We had a concentration of the production towards some very large production plants, production units connected at transmission level or at sub-transmission level. Those power plants were producing the power that was flowing toward the consumption interconnected at distribution level. While adding some new distributed generation as DG, of course, you are starting to create some power produced very close to the consumption, and that is creating, depending on the weather, because of PV or even wind farm, they are creating some bidirectional power flow. And this is having some very large issue with the power system. Okay, let's start with, at first, all the classical control might be completely challenged. The way I'm doing primary frequency containment reserve for primary frequency control, for instance, might be completely modified in the coming years. At second, we think about all the new uncertainties. Let's think that for years we had uncertainty in the load, of course, but now adding some uncertainties that are not correlated together with the renewables, uncertainty level is increasing. Then we have issue about voltage. Of course, connecting a PV plant very close to your house will, very close electrically, I mean, will increase the voltage level of the grid at your point of command coupling. That means that some of your appliances might get, let's say, older much quicker, and that is giving some very large issue about the load and the way we need to manage the voltage at distribution level. Then we have issue about protection. The fact that we are adding some new sources, themselves able to create some source of short circuit, it is changing the behavior of the short circuit current, and obviously we need to think about, are our protection scheme still correct to face this new distributed generation? Then, of course, there are issues about power quality. Typically, power electronic interface are creating some harmonics in the grid. And as well, if you have issue about protection, you can blind the protection, but you can have as well undesired tripping. And that is creating some new issues about the reduction of power quality in the grid, both at power quality level, harmonics, voltage, profile, sags, and so on, but as well at the continuity of service level. In this new landscape is coming a revolution that is called smart grid. So what is a smart grid? In fact, there is an issue because there is no clear international consensus on the term. And so from my viewpoint, and I'm relying on EU definitions, it's really a concept that rests on a system vision. And the system means power system and all the customers and everything connected to the grid. So as well, smart grid is usually really related to the electrical grid. At second, very important, a smart grid is not defined by the technologies that are embedded, but rather by what it can do. And so what we want to have, it's a digital energy network that can actively enable and integrate local and aggregated user actions, but as well automatic control energy flows to adjust, for instance, flexible energy supply and demand accordingly, and while trying to guarantee a more, and this sentence is very important, reliable supply of electricity in a cost and a resource efficient way. Okay, thanks to the definition we have now, we can put together things and say that there are finally three main pillars in the smart grid concept. First one is being able to push forward the accessibility for everyone. Accessibility is, of course, very often related to how much it costs. So you should be able to give a non-discriminative access to the grid and providing a full access to the energy markets. People should be able to do their business while selling or while consuming. And of course, you should be able to integrate the new uses. At second, you should be able to support the power quality at least as it is today, facing issues about your physical infrastructures that are more and more stressed with the uncertainties, but as well being able to safeguard any issues related to cybersecurity. Last but not least, of course, the smart grid should be able to support the sustainable development of your country, allowing more and more renewables being interconnected to the grid, reducing the carbon footprint of the different users, and trying to avoid as much as possible the different resources coming from fossil fuel. This can be achieved with two different families of solutions. Let's start with the first one. First one is related to the smart decision, smart operation. But as you are smart, you need to have the same intelligence that you should provide to the grid. But intelligence by itself is nothing. You need, of course, being able to take the good decision. You need at first to have sensors. The sensors are obviously for yourself as a human, your eyes, your ears, you're able to sense your environment. Those sensors are communicating information to your brain that will take the correct decision. So facing a lion, for instance, you will start to run. Whatever is the level of intelligence you have in the grid, a smart grid is still a grid. You need copper, you need transformer, you need devices, and if you want to implement some smart scheme to interconnect more and more renewables, well, obviously you need to have flexibility. And flexibility is as well something that is related to the architecture and operation scheme you have in your grid. So let's think about what the colleagues in Denmark did face when they had their energy transition in the 1980s. And at first what they created as simple solution was the fact that, okay, let's close some loops in the grid wherever it is necessary, so to increase the hosting capacity. And of course we can think about, okay, looping, but why not meshing, and meshing even more? So the architecture of the smart grid should evolve, and should evolve depending, of course, of geographical criteria that are usually related to the fact that you are not planning a grid the same way in the different regions, facing the different geographical constraints, but as well the fact that depending on what type of generation, the grid architecture might be slightly different. Aside from the two family of solutions I was describing, wherever you are adding some intelligence based on communication, of course, you are overlapping different infrastructures. The first one is the grid, of course. But then you need a communication infrastructure, and you need an information infrastructure. Both of them are more and more interconnected, and wherever you're having a growing interdependency with the other infrastructure, well, being clear, you are adding some new threats. So a smart grid is really an energy system of the numerical area that to some extent you can add some self-healing capability that is delivering electricity, that's the same for other energies, from generation sources, including renewables, of course, to consumption points. It should be able to optimize power distribution, facilitate bidirectional communication across the network, allowing the active participation of the final user, and trying to minimize interruption. But being clear, there are more and more relations between the different infrastructures. And so when one is failing, you can have cascading effects to the others. Having the ability to control smartly your network, in fact, is really needed is really related to your ability to communicating the information. And there are many use cases that are related to the new scheme of the way you are using the grid. That are, for instance, you want to support frequency. So you want to implement frequency containment reserve or frequency restoration reserve at distribution level, but very often you will achieve that using communication. As well, if you want to be able to solve congestions, well, communication again. If you want to support voltage profile deviation and to support those reactive power flow in the distribution and transmission system, of course, then you need to be able to coordinate the different regulating means to achieve the optimal, let's say, objective function that we'll describe later. You can as well have as target the ability to self-heal the grid or to push forward some new protection scheme based on wide area network communication. And if you want to enhance what we have today as market participation, well, for sure, you need to have bilateral communication between the different users, aggregators, market players. In order to make sure that the smart energy system will become a reality, in fact, you need to put together engineers, scientists coming from different fields and make sure that they understand each other. That's why the Smart Grid Coordination Group created a few years ago, aside from the FinCENI project, a 3D approach to cover domains, zone, and interoperability layers. So in fact, this is 3 different axes that are making sure that you are presenting any kind of smart grid use case in an architectural, but also as solution and technology neutral manners. So let's start with the first axis, that is the domain. Let's zoom a little bit. As a second axis, we have the zones. Third axis that are a different level of layers. In fact, the layers are really defining the interoperability and how it should be achieved. The different layers. So, thanks to the different layers, and we will illustrate that with one use case, you are using the SGAM to derive ICT requirements on the information and communication layers. So that's typically both data model and protocols, to identify the different interfaces between the different hardware components. Okay, let's now jump into the partial conclusion of this introduction. That's what we call take back home informations for you. Okay, there you remember the smart grid definition, and I think the most important point you need to keep in mind is the fact that this is a concept that relies on a system vision, and this is for the grid, and this is the added value should be always on the electrical side. I mean, only people for power system are able to compute what are the added value cost-benefit analysis of new functions. And at second, please remember that there is a real need in being able to model different layers related to different specialties to make sure that the different experts coming from different fields will be able to discuss and make the smart grid a reality. I would like to take a few minutes to present you an application of the smart grid architecture modeling to a given use case that I will call optimal coordination of active distribution regulating means. And at first, let's try to define what I call active components I want to coordinate in this smart grid. And obviously, the first one we think about is the concept of distributed energy resource. So there are different resources in the grid, for instance, distributed generation, storage energy systems, demand-side management, so the load, that are coupled, of course, with controllable power system equipment, namely on-load tape changers, capacitor banks, fax device, for instance. And so both endogenous components, grid components, coupled with exogenous components behind the meter, distributed energy resources, are called the active components inside the distribution system. And so to increase the deployment of distributed generation, very often with stochastic generation patterns, where there is a need in a coordinated control of the different components that should be able to deal with, of course, at first, the rising dynamics of the network, but as well with all the technical constraints that are arising. For instance, voltage profile deviation, uncertainties, congestions. So that's really an optimization problem. And since the stochastic generation cannot follow the load demand, because it is related to the weather, well, coordinated methods should be able to, for instance, help to know when to store the energy, when to run this specific load, and how to be more efficient, and how to create a grid that is really stable and resilient. So, in a nutshell, what are those components? And let's start to focus on the ones that are in the primary substation. In the primary substation, you will find on-load tape changers, capacitor bank, circuit breaker, and other devices that will help you to support the grid control from the point of coupling with the transmission network. At second, we are thinking about distributed devices connected to remote terminal units that allow you to change the topology of the network, for instance, while opening or closing some remotely controlled switches. This is typically the case of pole-mounted recloser, but as well other recloser stations you can find in the network. Then, of course, at secondary distribution network and secondary substations, you will find some devices that help you to sense, but as well to control, parts of the grid. Aside from the grid components that we already described, are the different loads you can control, but as well the different generation units that can serve as active components in this overall coordination of active components. The coordination can be seen with different points of view, and in fact the level of decentralization in the function you are creating for the smart grid is really an issue. Coming from the viewpoint that is there is one single coordination center, control center that is taking decision centrally for the overall grid, or if you say more in the spirit of the 61850, okay, there are different clusters of decision that can be achieved in the smart grid. In fact, those type of decentralization scheme should be proceed, designed, and carefully tested in advance to make the smart grid something that is reliable and efficient. Now let's come to the smart grid architecture modeling, and let's try to apply it to our system as it is today, starting with the lowest layer, that is a component layer. And at component layer, you find all the different devices. Let's focus on the distribution network distribution system operator is having. For instance, is having devices control devices at secondary substation that are helping to support some autonomous operation and that are communicating with primary substation to achieve a coordination. Those primary substations, of course, are communicating with the control center, and this is where the operator is taking the different decisions. But what about tomorrow? We discuss about much more active components to control. We are talking about components that are at distribution side, but that are at customer premise as well as distributed energy resources. So that means that the amount of components we have in mind is much larger. You need to include a control of generation and load, but as well any type of devices that are related to the fact that at low voltage level you have devices supporting the smart grid, for instance smart metering. You need to add new actors that are able to control devices behind the meter, and this is typically the landscape of the component layer we will face tomorrow for the smart grid. And if we push the dream a little bit further, in fact, component layer in the future might be much more complicated, including many, of course, devices, but many communication networks that can be public. And the different communication networks need to communicate through different, very specific actors, from aggregator, retailer, markets, together with, of course, the control of the distribution network, with the ability to communicate with the different primary and secondary substation, so to finally being able to target the active components inside the grid. At the function layer, now it's important, as mathematician, to set up what is the objective of your coordination function. And very often, what we take into consideration are the ability to reduce operating expenditures, OPEX. So for instance, you target, I want to minimize the losses, while of course respecting the different Kirchhoff laws, and taking into account technical constraints you have in the grid related to voltage, for instance, or related to power flows. Usually, to be able to implement some reconfiguration in the distribution network, technical constraints are not enough, and you need to add topological constraints. What does it mean? In fact, classical distribution networks should be operated radially, but are planned with some loops to have additional paths to re-energize the network in case of a failure. So being able to represent mathematically the fact that you want a radial network is usually related to the number of branches you need to open. And it's global number of branches minus number of nodes plus 1. In that case, you should open in the different lines that are represented here with the branches, you should open at least 3 switches. But in the example I'm presenting, as you can see, opening those 3 switches means that you will have one node that will be operated without any energy supply, and there is one loop. So in fact, you need to use classical tools from graph theory to find the fact there is only one unique path between the different nodes. At the business layer, of course, you need to make sure that your investment is worth for your money. If I say it in other words, any type of advanced function you need to create at the smart grid level should be cost efficient in some way that you will reimburse the money you will put in sensors, in actuators, and in coordination. So if you start with what I was proposing just before, you focus on network losses. Of course, you take into consideration operating expenditures. And that's very important to take it into account in the objective function. But it's even more important to have the ability to think about actualized costs in the lifetime of your different components, and to include both, of course, capital expenditures, your investment in the different components to make this smart grid function happen, and the operational expenditures, including the losses, but over the lifetime horizon. And it's really smarter. And this is one of the most complicated tasks for a DSO, to analyze correctly the cost-benefit analysis of any advanced automation functions that you will deploy. At the information layer, it is very important to create a way to have data models that everyone is understanding. So, of course, at first, at, let's say, market level, common information modeling is currently, through a standard, targeting all the different data models that should be exchanged between the different players. At the control center, classically, distribution system operators are still using common information modeling, 61968, that help them to put together all the different grid components in a dataset that is understandable by the different computers. When you go a little bit lower, starting in the field from the substation level, of course, there is one standard that is very well known, 61850, that is allowing you to have data model, logical nodes for different components. And that's a key to make sure that you understand who is who. This is clear for the distribution level, but this is clear as well for the DER and the customer level. Let's now jump at the communication layer and let's try to find out what are the best protocols to discuss between the different components. So I will not give the best, but at least some examples. So for instance, if you want to communicate between control center and primary substations, nowadays in the world, DSOs are mostly selecting either business as usual protocols they had before, sometimes homemade, but at standardization level, there are DINP3 protocols or IEC 60870. So TASE2, that is 104, that is IP-based communication. Between primary substation and secondary substation, of course, you can use what is proposed by the IEC standard 61850, such as web services or MMS communication. At DER level, of course, you can still use what 61850 is proposing for the level of MMS, but as well at the field level, that is of interest, is that 61850 is proposing you some communication at the so-called process bus, so the ability to communicate between control devices and sensor or actuators, so using, for instance, sample value measurements or generic objects for the substation. At the customer side, being clear and honest, there is still some ongoing work, and IEC 61850 was pushing a few years ago open ADR, but in fact there are existing many other possibilities to have internal discussion at the customer side and communication with the aggregator. Let's discuss a little bit about the benefits of using standard, and I will focus on the standard that is 61850. That is today very important for automation functions at the field level. So at first, they try to create something that is efficient. You want to have something that is self-describing the different devices, so to reduce the setup time, and so saving some costs, of course. You want to be able to reduce all the wires, and this is possible because you are creating communication between devices with a common backbone at primary substation, but not only. And it is efficient as well because it is using some standardized naming convention. So instead of numbered, registered, or tags, and to increase the understandability and reduce commissioning time. So let's focus about what DNP3 will use. It will use number of IED, the number of objects, the number of variable, and the value. IEC 6150 is using a convention so that there is a unique way to describe a given value. This is still very, let's say, verbose, but is giving really something that is simple. At second, of course, you want to be interoperable. Why it is important to have interoperability in a smart grid? It's because, in fact, you will have the ability to buy some solutions and devices from different manufacturers. It will reduce the cost because it will increase competition between the different producers. And so, using IEC 61850 is really using an IEC standard that is widely adopted across the industry. The device description is using standardized object models. And for the configuration, you're using XML file, for instance, SCL, to describe the devices and the functions at substation level. And as well to describe the substation architecture, the ID contents, the communication between IDs. This is something that is really much more detailed than you can have in common information modeling that you're using at the SCADA level. In fact, everything about this way to describe the different devices for configuration is detailed in the 61850-6. This slide is providing an example of this configuration file called SCL, just as an example of how I'm describing a substation that is from 110 kilovolts toward 33 kilovolts. And so that's typically what you find with XML description and tags, so to describe completely what is in the substation. For the data model and the structure of the data model, what is important is that this is hierarchical. It can be represented as a tree, starting from the physical device that is having a network address, communication network address, and that is including inside some logical devices and logical nodes that are slowly by slowly storing some values for the different variables. And for the mapping profiles, what is interesting to see is that the 6150 standard was describing some different services that are either at level 2, so at MAC address level, namely typically sample values and GUs are typically some way to exchange data between the different devices. You have, of course, the necessity to have time synchronization that can be done with SNTP, at least for the classical functions you want to have. And if you want to discuss between the different devices, you can use client-server services So for instance, and I was already giving the example of MMS protocol. So as a summary of the IEC 61950, there are different parts of the standard that are from the introduction to the description language. I was giving an example just before. There are different parts that are very important to know in order to be able to implement in the different intelligent electronic devices and in the different functions interactions between all the different devices. Let's now jump to the partial conclusion of this part and take back home information I want you to keep in mind. At first, a coordination algorithm can be very complicated, and you can rely on some very advanced optimization methodologies, such as quadratic programming or second-order cone programming, those fields that were opened by Parivar and Lowe a few years ago, colleagues from Berkeley, that are allowing you to reduce, for instance, losses while still trying to apply some linearization scheme to have optimization very efficient, even if you have a problem that is non-polynomial difficile, but thanks to reformulation, you're able to have very efficient algorithm for the coordination. At second, what is of interest is that the smart grid architecture modeling can successfully show the missing coordination part between feeder automation, 61850, so power utility automation, and the SCADA data model, that is the common information model, that is usually for at SCADA level to manage the energy and the network from the operator point of view. Let's now jump to the conclusion of my presentation. So, in order to enhance coordination within a smart grid, in fact, you need to have efficient communication infrastructures. And clearly, public communication infrastructure, such as Internet or future Internet, will be, thanks to some new generation of communication, 4G, 5Gs, they will be able to propose enough quality of service to allow future specific coordination scenarios. And power utilities will be more and more aware and cautious of the service that information technology utilities will provide, telecommunication companies. And they will, of course, be more and more able to size the service level objective, SLO, that are really, it's typically the quality you want to have from the communication infrastructure, so to serve service level agreement, so your ability to communicate between one component and one other. At second, the communication infrastructure is interacting between different layers that are composed of different specialties, engineers, business scientists. And this is thus why we need a clear methodology that is proposed by SGAM to assess interactions between layers, and thus engineers that will discuss together, even if coming from different fields. And those interactions, if they are badly size-tuned, can really weaken the whole smart grid. So my presentation is now over. I hope you appreciate the different information that comes with. And just to remind what were the learning outcomes I had in mind. So at the end of the lecture, you should be able to describe the smart grid concept with the three revolution paradigms. So evolution in operation, evolution in structure, and of course the issue about more and more interaction between the different infrastructures. You should be able to list the axis of the smart grid architecture modeling concept. You should be able to select the relevant objective function. For any type of advanced automation function your boss will ask you to do. But for the same function, of course, you should be able to select, to support the selection of relevant protocol and data models. You should be able to discuss the relevant business case. And you should be able to build the various layers for this function. Okay, thank you for your attention. I hope you appreciate the journey. And I hope now you are more and more able to assess what are the real needs at communication level, at function level, as business level, to ensure that tomorrow smart energy system will be a reality.